Welcome to the webinar, Impact of Human Factors on Operator Response to Alarm, Lessons Learned from Process Industry Incidents. This presentation has a lot of material, so I'm not sure we'll have much time for questions at the end. So what we'd like you to do is enter your questions in the questions box along the way, and then we will collect them afterwards and get back to you. So my name is Todd Stauffer. I'm the Director of Alarm Management here at exida and have been involved in the creation of the alarm management standards that govern industry. And I'm going to turn it over to my colleague, Peter, to introduce himself.
Thanks, Todd. Hi guys, Peter Culbert here, Senior Safety Engineer with exida out of the Ireland office. Basically specializing in automation controls, maintenance and project management, stuff like that. Current focus is functional safety and basically helping our clients achieve their goals through cyber and alarm rationalization as well.
Excellent. So this is my first collaboration presentation with Peter, so we're looking forward to it. A little bit about exida. We were formed back in 1999 with a goal to make the world a safer place. We initially focused on functional safety, but expanded that into other areas of risk like cybersecurity and alarm management. We're one of the leading companies for certification, particularly in the world of functional safety. In fact, if you've ever designed a safety instrumented system and put together a safety instrumented function with SIL rated equipment, chances are it was exida that did that assessment. We've done more assessments than any other company. We also have a suite of software for safety instrumented system design that helps you follow the whole entire functional safety life cycle. Included in that tool is an alarm management module called SIL Alarm. So what are we going to talk about in today's webinar? We are going to focus on how humans process information and make decisions. And when I say humans, I mean in particular operators. So we are going to look at some of the key human factors elements that impact that. We're going to apply that then by looking at some incidents in the process industries and see what we can learn in terms of understanding of why those incidents occurred based on human factors, and see what we can do differently to help prevent them in the future. So one of the motivations for this presentation is the fact that over the last 30 years or so, the number of occupational accidents, occupational safety, slips, trips, and falls has definitely decreased, but a similar reduction in incidents has not been seen in the process safety world. And actually now we're starting to definitely see repeats of incidents that have happened in the past, indicating that we're not really learning as much as we could or as much as we should from the incidents that have occurred in the past. So that is one of the goals of this presentation. Also, from a purpose point of view, if your goal is to look for deviations from operating procedures and behaviors that operators did, or to look at assigning blame to humans and operators, then this is not the presentation for you. That's not what we're looking for. What we're trying to do is to better understand the mechanisms and factors that shape operator behavior under abnormal situations, and in particular, to better understand the context that shapes operator performance, how they make decisions and take actions. So with that, let's talk about some human factors basics. First, I want to talk a little bit about how information is processed. We take in information using our senses: sight, sound, smell, touch, and the first part of information processing is to understand what those senses mean, or what we're receiving. We're encoding those perceptions. And if you look at this drawing, you can see that there is a line that goes directly across from perception to response. So that means there are some things where, just based on noticing what is happening, the operator instinctively makes a decision, takes an action. They don't have to think about it. We're going to talk about that later as a skill-based response. Doesn't require a lot of mental energy to do that. In the second case, we see in the perception box, we're actually leveraging what's in our long-term memory. We got to think about it and leverage or access the experience that we have from the past to be able to better understand the context of that new cue that just came in. And then based on that, hopefully we've got a memory that helps us know what to do, and we can again take that corrective action relatively quickly. In some cases, though, we really need to actually put a lot of thought into it and understand what's happening, try and diagnose the problem, maybe do some simulation in our mind of what's happening or what would happen if I take action. So in that case, we're using our long-term memory and our working memory, and that becomes very resource intensive. And it's based on that thought decision that we make as we think about what to do, that we take our corrective action. So one of the things to notice is that there is really limited resources for information processing and these other cognitive activities. So the more you can execute through this almost unconscious path, that skill-based execution of tasks path, the less energy we use up and the more that we have for addressing other tasks. So there is limited energy for cognitive processing. The other thing to notice is that there's a feedback loop. So particularly for expert operators, they will take a corrective action and then they will monitor what happens to see whether they need to make a course correction. Now let's look a little bit more at how different types of responses occur based on the operator's level of experience and expertise. So first, at the bottom, we talk about what's a skill-based response. This is that unconscious automatic response that somebody who's truly an expert does. They don't even need to think about it. They see what's happening and immediately can take the action without doing a lot of mental processing. It's also called level one thinking in the books by Daniel Kahneman. So it's a really quick action, and again, it doesn't require much in the way of cognitive resources, but you have to be experienced and an expert to get there. The second scenario is a rule-based application of information processing and action. In this case, you do have some experience, you're somewhat familiar with the task, but you're not an expert. So you have some kind of rules in your mind, some patterns as to how you might react. So you need to try and figure out what is the right rule set to apply in this case. So you are putting in some thought, but you do have some ideas on what the right thing is to do. So you apply those rules, and then that guides the action. The last response model is what's called a knowledge-based model. So in this case, the operator doesn't have significant experience with the task or the situation. So they really have to put a lot of thought into understanding what is happening, to diagnose the problem, and to figure out what the appropriate corrective action is to take. So a experienced operator will spend most of their time in the skill-based behavioral realm. However, depending upon whether they encounter new situations that they don't experience for, they may also end up responding from a rule-based or a knowledge-based point of view. But most of the time, experts are responding from a skill-based point of view. So Why is this important? Well, it also guides the type of errors that can occur depending upon your response pattern and your level of expertise. So, for example, the skill-based application of knowledge and behavior, if that's what the operator is using, then they are subject to errors such as slips and lapses. Now, those relate to situations where the operator knows what to do. There's just something occurring in between the formulation of the action and the actual execution of it that's getting in the way. And we'll talk about that more in a second. But this is what happens potentially to experts. They know what to do, but they may make a mistake. Sorry, not, they may hit the wrong button, for example, or they may forget to close out something to complete it. So they knew what to do, but they didn't complete it successfully. Now, in the realm of mistakes, this is where less knowledgeable operators fall into and succumb to errors. So we talked about rule-based applications. This is where you're trying to match a scenario that's happened in the past and respond accordingly. So if you think the wrong rule is what should be applied, that can result in an error, or you can apply the rule incorrectly, and that can also lead to an error. And then a knowledge-based error is when you really don't have enough experience or knowledge or understanding of the situation, and you make an error because you don't really have a good handle on what to do. And then the last type of error is what's called a violation. That has kind of a negative connotation to it. It doesn't necessarily mean something bad has happened, but what's happened here is the operator has deviated from expected procedure or behavior. Now, there's a human factors element called the law of least effort, which basically means humans will always try to figure out a way to do something with less effort. So a violation could just be the operator trimming off a couple of steps, trying to make the process go quicker. So it's not necessarily a negative intent. Now, part of the reason why this is important then is in trying to figure out how we address these situations based on the type of error and the associated experience level of the operator. So if we look at where mistakes happen, those are for less experienced operators. That happens when they are interpreting the situation and when they are planning the appropriate action to take. Experienced operators, their errors occur as they access memory to remember to do certain things and in the actual execution of the intended action. So why is this important? Because training, for example, which would be a typical remediation or corrective action, that works well for mistakes for operators that are not as experienced, but training does not address slips and lapses. Those kind of errors are not addressed by additional training, and in fact, can have a negative impact. If you force an experienced operator into additional remedial training because they made a slip or a lapse, it's not going to help, and it may actually have a negative impact. Now, to address those slips and lapses might require some changes to the operator interface in the way things are laid out, the information that's processed side by side, or potentially the addition of some job aids to prevent these slips and lapses from occurring. So there are definitely design techniques that can be applied to minimize the slips and lapses, which is what the expert operators are prone to. Now, those aren't the only sources of error. There are cognitive biases as well that impact or get in the way of successful decision making. The first one that we're going to talk about is recency bias. That's people tend to overestimate the importance of something that has happened recently when they're trying to figure out what they should do. Another important bias to understand is confirmation bias. This is something that everybody does. When you find a theory of what has happened and what you think should be done, as you take in more information or seek out more information, oftentimes you can just look for information that reinforces what you already think. You don't process or you don't look for information that disagrees with your original theory. Obviously, that can lead to some incorrect decision making, so we need to have a handle on when that occurs and why it occurs. Overconfidence is another cognitive bias. If you've ever heard the saying, 75% of people believe they are above average drivers, can't be true based on statistics, but it indicates that oftentimes, and this is something that experts fall prey to, is they believe that they understand the situation so well and that they must be right that they can tend to make errors that way. And then the last one I wanted to mention was hindsight bias. This is when we look back at situations that have occurred in the past and we conclude that they are much more predictable than they really were. We think that in hindsight, the operator should have done this action or should have been able to connect the dots here, when in reality, if we put ourselves in their shoes in the heat of the moment, that would not be a true assessment. So now let's see how that all factors into what the operator deals with and how they process information. And at a high level, what they are trying to work with is situation awareness, and they need situation awareness as a key element of successful decision making. So they're taking in cues and trying to understand what they mean, perceiving them, using their mental models, their understanding of how the process works to kind of project out what those cues mean immediately and in the near future. So if an operator has good situation awareness, they have a good handle on what is happening with the process, where it is going, and where it will likely head to in the next, let's say, 20 minutes to 30 minutes. They have a good handle on what's happening. Now, the mental model is what the operators use to kind of, in their mind, understand what's happening in the process. So it captures the understanding. It helps guide them on what to do. It helps guide them on how to understand what's happening. If the pressure goes up, the temperature must go up too. It helps them fill in missing information and helps them to be able to do mental simulations to try and predict what's going to happen if I take a certain action. So it's a really important thing for them to be able to work with to respond successfully. And the more experienced operators have better mental models, as you would expect, of a situation than a less experienced or junior operator. So to finish up this section on human factors, the last thing to talk about is how do humans or operators make decisions in really critical situations when the crap really hits the fan. Now, you might think that most decision making is very logical and rational. You flesh out the alternatives and rank them and score them, and you take time to pick the one with the greatest value. Well, that may be what's done sometimes, but in the heat of the moment, that's not the way people typically make decisions. What they found by studying people that work in the ORs, nurses in particular, firefighters, they follow what's called a recognition prime decision model. So they basically look for patterns. They look at what they are seeing and reference it to past experience. And based on that, they formulate a plan on how to respond. So they are using their intuition, they're using their gut feeling, they're matching patterns based on what they've seen before. And they don't do an extensive analysis of different options. They essentially go with the first option that looks viable. And then they refine that over time. They do mental simulations of, okay, if I do this, this is what's going to happen, or if this is now changing, this is different from what I expected. Now I make some course corrections along the way. So that's the way experts respond under critical situations. So an expert operator would respond that way. A junior operator or a new operator would struggle in that kind of situation because their first option that they come to might not be a very good one. So with that, we're going to transition now to Peter's going to talk about operator response to an alarm.
Thanks, Todd. So this section, guys, is to just capture the operator's response to an alarm, to follow on from what Todd said, and how that affects the overall safety of our process. So just to start, just a couple of case studies from the HSE website in the UK. An LPG tanker broke away from its moorings in high winds, started to drift away from the coast. Vessel wasn't damaged, no injuries, but the overall incident highlighted a problem with the alarm systems and how the operators were responding to those alarms. In this case, it was found that the operators were routinely disabling the wind speed alarms, as you know, as any one of us would kind of appreciate that when the wind gets up and then goes back down again, the alarms are probably coming on and going off. So the justification on their end was for that reason, but they suppressed the alarm, and in this case, this was leading to potential damage and potential harm if anybody had been on board the vessel itself. So it's a real kind of eye-opener as to, whilst it is inconvenient to have an alarm enunciating all the time from a typical operator's perspective, it is there for a reason, and in this case, they were quite lucky that it didn't develop into something more. Second incident, basically a flare system. For anybody out in the oil and gas industry, they'll be familiar with that. The pilot lights were extinguished. It happened because there were fluctuations in the gas supply to the flare. Very dangerously, a gas cloud formed, and unfortunately didn't ignite. But when the installation was restarted, it came from an installation which has been restarted in this particular instance, and I think a lot of people would have seen this as well, that on a restart of a system, you'll get all of the alarms, including previous outstanding ones that are, for isolated equipment, things like that. And because of that alarm flood or alarm blizzards that came in, the actual operators failed to detect the alarm for the flare. So again, right down to exactly what Todd was saying about how humans will process information and things like that. So in this case, 3,700 alarms is going to be too much for any typical human to process. So how operators respond to an alarm, and what makes for an effective response. So how, typically we would be looking to try and model ourselves if we're in those shoes, and how would we look to try and, make sure that the process goes through the right steps. So we usually detect, and as Todd was mentioning, with our sight, with our hearing, we look to detect, like a sensor does, any kind of change in our environment or things that will alarm us and draw our attention to that. Just like a logic solver, we then would begin to diagnose. Why has this alarm gone off? What should I be looking to do? What is the process deviation? Does it require action? Is it something that has happened outside and on the field, or what is it required of me at this stage? And then typically, as we see in a final element stage as well, we need to respond. So take an action. There's a reason why the alarm went off. Follow it up. Diagnose why the alarm went off, and take an action and respond to any process deviation that may lead to an unsafe scenario. So just to highlight the bottom, poorly performing alarm systems and HMIs impact all steps and operator situational awareness. So as we referenced in one of the case studies earlier, just in the previous slide, if the alarm or if the HMI has not been set up and designed with human factors in mind and the end user operator in mind, you will not get a streamlined process of detect, diagnose, respond correctly, because the human won't be able to process all of that potentially unnecessary information to take the required action in the required time. So just move to the next slide. So the typical operator response to an alarm. So this is, the typical red flags that we would be looking at in an operator response to alarm. So this isn't, what an operator should do. It's typical red flags to watch out for. So, acknowledge the alarm to allow for concentration on the process task currently ongoing, and that would be acknowledging without follow-up action. So if there was an alarm and it was continuously enunciating, the operator acknowledges to allow for concentration on other tasks that he's doing and doesn't follow up. Attempt to diagnose if some action taken has caused the sudden appearance of an alarm. So the operator has received an alarm and he's detected it. Usually the first reaction is, what have I done? As we see here in the next bullet point, what have I done? Am I in trouble? Has something that I've actioned in my process caused this alarm? These are the typical, mental processes that the operator would go through. Again, they would start to ask themselves, have I seen this before? And how did I get rid of this particular alarm on the previous occasion? And like Todd mentioned, the mental models and the patterns that start to form, and especially with experienced guys, once they can process all of this stuff quicker, they, I've seen it in the past, they can tend to go straight to the shortcut of how it actually, we got rid of this alarm before. And as Todd mentioned, that could lead to an error also, because it might not be, in this case, the same as it was in the last case. So that's something also to watch out for. And typically operators, especially if they have to go out into the field and investigate, resetting the current alarm, and if it ceases to enunciate, no need for a follow-up. These are red flags, that we've all seen, certainly in the industry, across various industries, where if the operator, especially if their cognitive load is reaching the maximum for that particular scenario, if the alarm goes away, they tend to not follow up, not investigate, and that's not a mistake. It's not something that it's done with malice. It's just simply because humans have a certain cognitive load, they can process so much information, and they'll prioritize different things subconsciously. So, things to watch out for, guys: reporting culture and stuff like that. Any alarm, it needs to be followed up. So typical problems for the operator with the alarms. So, from the operator's perspective, what would the typical red flags for them be that would impact their response being the correct one, and also them responding in the correct time? So alarm floods, like we spoke about earlier, that those 3,700 alarms, and operators unable to diagnose and prioritize correctly due to poorly rationalized alarm database. So something we cover on our alarm course is it necessary information for the operator, and does it require him to take action? If not, it's usually not something that should be in his alarm database, because it's extra processing that can take away from the response time for the operator and can ultimately lead to an incorrect decision or an unsafe action. And as I said, their operators run out of time to take appropriate action. So if the alarm floods are there, the operator is trying to make sense of everything that's in front of him, and he's trying to prioritize what should he do in which situation, and time is running out, which is critical in these situations, guys. Alarm masking, psychophysics. So audible enunciation is not heard above the typical site background noise levels. So, in an environment where there's some noise in the background, some, ongoing works or whatever, it's, the operator needs to be able to determine and detect any alarm above that background noise and above his minimum threshold of detection, which is what psychophysics will, we can go into that later as well in another slide. Visual enunciation, not visible due to poorly designed colouring of HMI screens or alarms, depending on the colour of the prioritisation. And the environmental lighting levels. So from a human factors point of view, have we looked at the lighting levels in the area the operator is going to work with, and can he detect any change in colouring on his HMI screen from an alarm if there was no audible detection available? Would he be able to detect that, and would it catch his attention? So further typical problems for an operator with alarms would be nuisance alarms. This can lead to a term called normalization of an alarm / process state due to constant reoccurrence, and that would tie back into the case study that we saw earlier, where the guys eventually suppressed the alarm, which is the wrong thing to do, obviously. But in a normalization scenario, if there's an alarm that's constantly the same alarm, and somebody has maybe passed the information on, no, that's always the case, operators tend to normalize that, and they'll just get into a habit of maybe just resetting it and not following it up as it should be. And we can look at an example of that later. Also, an operator interference in alarm threshold setup, just to avoid the nuisance alarm. If it's audible and it's annoying to the operator and it's interfering with his other duties, concentration levels, stuff like that. Sometimes operators might look at adjusting the threshold to bring it within the tolerance so that it no longer enunciates. And again, seen it in the industry, guys, in the past, this can get forgotten to be handed over, and suddenly, because it becomes a behavior, it becomes something that's acceptable in the culture, and all of a sudden your threshold has moved to a dangerous level simply because of an enunciated alarm, which could have just been some equipment that needed to be calibrated or followed up on. Poorly designed alarm text, classification of priority, another thing we cover in our alarm course. It can lead to poor decision making and human error. Also misleading the operator, and be solely responsible for initiating the event. So the text that appears to the operator has got to be clean, crisp, and give him as much help as possible so that they can go and action any process deviation correctly. The classification has got to be right, and the prioritization has got to be right. So, and as we said earlier, not all information needs to be presented to the operator, just something that requires him to take an action. So typical human factors affecting operator response. So we would just highlight cognitive load, as Todd mentioned earlier. Competence is a huge one, guys, because you can have operators that are many years in the business and have spent lots of time in the industry, and they still may not be competent to carry out the duties required for a particular system, with a particular system, and with a particular process. Psychophysics, as we mentioned earlier on, where you're looking for that minimum threshold, the smallest change in stimulation volume within the environment. And that can be different for all operators. All humans would have a different detection level in that. The usability of the devices the operator is going to be using. As we can see with poor Homer there, that kind of setup looks pretty daunting to anybody to try and find out how usable is that terminal. And in a lot of cases, HMIs and designers can be, all the best will in the world to put as much information there for the operator, but is it usable? Is it something that's very obvious when the operator goes to use it, what he has to do and how he can take an action safely? We'll look at performance shaping factors, various different factors that will affect the performance of the human in a situation, and organizational culture. I think everybody will probably have a lot of experience with that also. We'll look at that and how that can affect your operator's performance. So cognitive load, too much information to process at once, alarm floods, multiple responsibilities, multiple HMI screens, etc. So everybody's will be different. What is the cognitive load for a particular operator in a particular process, and have we overloaded them in that process? If we're requiring our operator to be a supervisor, as we're seeing here, increased levels of responsibility in parallel task management at the site. So if we're expecting our operator to be a supervisor or manage various other tasks, we can't also expect them to look at 6 to 8 HMI screens plus, who knows, 3,700 alarms as well, and expect them to make the right decisions in those moments. So if we're in if we're going to be looking at it from a human factors point of view, which we should at design stage, we should take these things into consideration and have a look and see if we've got the right amount of load for the operator before we put him into operation. Is there too much data to process at the HMI screens? Again, alarm floods. How much information are we presenting to the operator, and does he really need to see that? Is the operator competent, trained, and experienced enough to prioritize correctly when the cognitive load is exceeded? So at that threshold, when we've reached cognitive overload, is the operator reliable? Is he competent, trained, and experienced? And that comes down to, have we provided the right training? Have we provided the right facility, the right systems, the usability of all of this stuff? Have we put the operator into the right environment to make sure that we've optimized the efficiency and performance when the cognitive load is exceeded? So competency, lack of appropriate level regards to operator competence. Operator is unfamiliar with alarm philosophy documents, alarm operator response documents. So in that case, like I said earlier, we've got a case where an operator is many years in the industry. Everybody knows it's a senior member of the team, but are they familiar with our alarm philosophy document? Are they familiar with the responses they need to take for each particular alarm? And this is key, guys, because even if it was 2 alarms, if the operator doesn't know how to respond to that particular alarm, they're spending a lot of time trying to figure out and diagnose what the correct action is. And that's key time that you can't afford to lose in an emergency situation, for example. Operators being placed into operational scenarios before, and they are ready for the position. All comes down to competency. Have we got the right competency? Have we got the right operator in the right position? Have we looked at that? Have we assessed the right people for the right job? Training is not being provided on the specific equipment or systems in use to refine the operator efficiency and his understanding of his role in an alarm response plan. So training has got to be provided as well. It's got to be honed, it's got to be current, it's got to be ongoing to make sure that it matches each different deviation of our process as we go along, so that we can have confidence in the reliability of the operator in these situations, and so that they can be confident themselves that, you know, in every alarm that they see, they're confident they know a response. And then, as Todd was mentioning, they get to form these mental models. They see patterns, and they can start to increase and take these decisions with a quicker and more confident, role. Is there a competency management system in place? Are the assessors competent to be assessing the operators within the framework? Also very key that the people assessing the operators are also competent to assess those operators, that they're not just signing these things off just to meet some organizational pressures. They have to be competent themselves to assess the competency of others. And are the assessment procedures verifying both knowledge and understanding of the requirements for the role? Very important as well, guys, that if we are assessing people for competency, we're not just assessing that they're able to follow X, Y, Z steps correctly. We're assessing that they can apply the knowledge and that they understand the knowledge, so that they can make the decision correctly of when to apply that knowledge and when not to apply that knowledge. The last thing we need in certain situations, to take an example in the oil and gas industry, if there was a scenario that developed and it was called for to make a decision whether to shut the well or not to shut the well, you can appreciate those are very important decisions for safety and for financial impact to companies. So we need a competent operator that knows the difference and understands the knowledge that he's been trained with of when to use it and when not to use it. Psychophysics, just to explain, and this is straight out of Wikipedia, quantitatively investigates the relationship between physical stimuli and the sensations and perceptions they produce. So you're basically, like we explained earlier, looking for that minimum threshold detection level that an operator or a human can detect a change in the environment, and that will be different for everybody. So that's why it's key to engage the end user and the human that will be involved in the process at the design stage, so that we can find out what these thresholds are and make sure that we're well above these, so that it's an easily detectable alarm that we're designing. So have the HMI screens been designed in such a way that the operator can easily differentiate between stimuli and the background color. We covered that earlier. We've got to make sure that we're not putting very bright colors in there and then keeping the lighting very bright, and the guys won't detect anything if there's no audible setup. So just to continue with audible, have the audible enunciations been set to above the operating environmental stimuli, i.e. background noise, and to a sufficient level to stimulate detection and action from the operator. So we've got to make sure that we've set it up so that it's detectable above the background noise, above any other environmental stimuli that are there, so that the operator can detect it as quickly as possible, which gives him time at the other end to make the right decision and effect a change before we have a process safety incident. So are the alarm enunciations, both audible and visual, designed with human factors in mind, and are they sufficient enough to be easily detected in the environment? So just to highlight that we need to be engaging the end user, and it's a specific requirement. You know, every human is different, so just to try and highlight, we need to look at both of those there. So usability, Norman's good design practices. I'm not sure if guys have heard of that or not, but how do we apply Norman's good design practices to our operator responses to alarms? So is it clear to the operator what all the options are in an alarm situation with the HMI in use? So for example, if there's an alarm there and we covered it with, you know, the text, let's say the text isn't great, it's open to interpretation, maybe hasn't been designed very well. Is there an alarm help option there? Is it visible? Can he see it? Does he know which screen to go to next? Are all of these things visible for him and easy to use? Feedback, so does the system present an appropriate and clear response to the operator when he acknowledges an alarm? And can he progress to the next appropriate step? So is the system giving him feedback of every action that he takes? And does it present him with a clear response when he does take that action? Affordance, so has the HMI or the alarm been designed in such a way that the operator can quickly and efficiently migrate to the desired option and process action within that system? So affordance is basically, in our design, have we made it as easy as possible for our operator to migrate through the various objects and screen layout within the HMI that we've set up for them, so that it's not cumbersome, it's not something they have to go and look for. And again, that comes down to training as well. But when we're designing it, we have to take the usability into account, not just wait for the operator to feed back to us that it's very cumbersome. You should be engaged at the design stage and try to get these things out of the way then. Mapping, have the HMI screens been set up to highlight clearly the effects of any operator action within the process? So, you know, animations, instrumentation, bar graphs, things like that. So if an operator does take an action, you know, he closes a valve or something like that from the HMI screen, can he then see that that action had an effect on the HMI screen in relation to the process? So that we've got to be able to show on our HMIs that any action that they take has been mapped, and he can see that the action has had an effect on the process. Constraints, so have the HMI screen options been configured with the appropriate constraints? And this is basically, guys, to prevent an operator inadvertently causing further potential, you know, hazards. So we would look to see what kind of constraints we put within the system, interlocks, passwords, messaging would help, so that the operator can't cause further process safety issues just by having a full-blown effort and not really knowing what the actions are going to take if he was to start playing around with the HMI. So have we put the appropriate constraints into our design? And consistency, have the HMI screens been designed so that every operator input to any HMI object produces a consistent output and a result? And this allows for, as we were making the point earlier, for patterns to form, so that the response time quickens, and the operator gains confidence in the HMI and the process, and we effectively get a more reliable situation. So performance shaping factors. So the equipment design can sometimes be cumbersome, not very easy to use, can affect the performance of the operator in an emergency situation. Working environment conditions can have an effect on how the operator performs in an emergency situation. Back to noise, psychophysics. Organizational culture and procedures can influence the decision making of an operator in an emergency situation. So that could be out-of-date procedures, organizational pressures, etc. Personnel stresses and relationships within a team can also influence the operator's decision-making process in an emergency situation, and that could be down to supervision, personal interrelationships. And fatigue can play a major part in operator decision-making also. So, typical things like, 12, 13-hour shifts, length of the hours worked, the travel, things like that. Organizational culture. So are the staffing levels correct for the task responsibilities? Is there clear and definitive procedures for each task and situation? So alarm philosophy documents, alarm response. Is the culture among operators to just silence the alarms and not follow up? What is the reporting culture like? Do operators escalate certain alarms to be investigated, or do they just leave them? Should always escalate to maintenance and whoever the responsible parties are. Is the organization adopting a dynamic competency management system to ensure the correct personnel are executing in the correct roles? So that's not just a competency effort at the start, guys. When we deliver a project, it's a dynamic, continuous life cycle effort to make sure that everybody is competent with the increased change in equipment and personnel. And are the organizations providing the latest and up-to-date training for the operators with regard to those equipment and systems and emergency response scenarios? So human factors engineering, this would be basically at the front end, guys, incorporating human factors into the design of a product, layout, system or facility. Very important, engaging the end user of the product or the system under consideration at all stages throughout the life cycle. Consider the human factors when drafting your organizational procedures for operational tasks, and continuously assess human factor conditions throughout the life cycle of the system, product, or indeed the operator. Very important to consider these things and not have them, fed back after an incident has happened on the site. So just to quickly move into the review of some incidents, and as Todd mentioned earlier, this isn't in any way a hindsight armchair exercise to point out, well, I wouldn't have done that this way, or things like that. What did they did wrong? Not at all. This is basically why it made sense for them to act the way they did. Because if we don't try and understand why the human in the situation acted that way, then it's entirely possible for that situation to happen again. Too often in industry, there's a blame culture, and you don't ever remove the incident or the reason for that incident. So just a quick first example, an offshore facility. So a drilling process was ongoing, utilizing multiple hydraulic equipment. If anybody's familiar with the typical drill floor, you'd see a lot of hydraulic equipment moving around, manipulating pipe and assisting in the process. So the main HPU fluid registered a low-level alarm at the time for the operator. Then shortly after, a low-level alarm due to a leak in the hydraulic system. The operator acknowledged both alarms without escalating or taking action due to the workload that was ongoing at the time and multiple tasks and responsibilities. So the alarm was acknowledged and silenced, but there wasn't a follow-up action taken. Hydraulic oil level reached critical low level. Multiple equipment started to lose hydraulic oil and was starting to fail. And essentially the low level safety switch caused the shutdown of the main HPU pumps control system, and repairs were initiated. Now this was at a 15% set point, so you can imagine that that's an awful lot of oil to lose, and there was an urgency at that stage of the incident itself to stop the process and to try and put some hydraulic oil back into the system. So what are the lessons learned with this, guys? So why did the operator acknowledge those alarms without follow-up action? Lack of competence, knowledge and understanding. So that was what we were stressing earlier. Competence isn't just, does he know what to do in that situation? Can he functionally acknowledge the alarm? Yes, of course he can. He can click on it. But does he understand the ramifications of the alarm, what it's about, how it's affecting his system? If he loses hydraulic oil, might not be able to hold the drill pipe, might not be able to manipulate the drill pipe in that process that he's in. So did he understand the level of acknowledging the alarm and the repercussions for that? His cognitive load exceeded, alarm flood, multiple tasks. In this case, the alarms were multiple. There was a lot more alarms than just this one. And there was a bit of a culture of just acknowledging in this particular case to try and see a more fluid alarm banner And I think that multiple tasks and multiple responsibilities, you know, like we mentioned earlier, humans can't process all the information at once. They can only process a certain amount. So this, unfortunately, was the one that had to fall through the net. And environmental conditions, noise, distraction, people looking for that person's attention as well. So why was it possible for the operator to acknowledge the alarms and the system to continue operating? So why was it possible for the operator to acknowledge it? No follow-up action taken, and why did the system continue to operate to a 15% level? So when the investigation was carried out, it was incorrect classification of alarms. So these alarms particularly weren't classified as safety critical. There was incorrect prioritization of the alarms, the color code and things like that. Whilst he did detect it, it wasn't prioritized correctly. Incorrect system constraints in the design. So the control system was not designed to stop the process or you know, constrain the operator to force him into taking further action in this case. So if, you know, and we cover this in the course as well, all of this stuff should be looked at in a design stage so that you don't end up with a potential process safety incident. Second example, guys, another offshore facility. There was a fire and gas repeater panel in a driller's cabin. The safe area low pressure alarms were detected on a daily basis going into a high H2S well. So the repeater panel would have been alongside the driller in this case, and the alarms were for fire, gas, and low pressure in safe area alarms, which would have been critical to that particular hazardous zones applicable. The alarms were investigated. The operator would have sent out you know, some of the team members to investigate the alarms and see if there's anything going on in those zones. And the process field conditions were confirmed as safe. So the operator continuously reset these nuisance alarms. They then became nuisance alarms to the operator, being that they were audible as well. And this became the culture for a period of time. And then follow-up proof testing identified incorrect fire and gas panel HMI identification as per field equipment and location. So when this was followed up because of these alarms going off and it was investigated why are they continuously going off, it was found that the repeater panel in this location was not displaying the correct field equipment on the HMI itself. So it was put down to a replacement part that had been put in and hadn't been fully validated at the time due to, I think, access requirements. And the replacement part didn't have the appropriate HMI tags allocated to the field equipment. So the operation was stopped. A software upgrade was carried out and followed up with validation testing and some calibration as well for field instrumentation, as that had been found also to be wanting in that scenario. So lessons learned from this incident, guys. When an alarm becomes normalized by an operator or designated nuisance due to malfunctioning equipment, the process should always be stopped and full investigation carried out, which includes validation testing. So in this case, the guys were normalizing the fact that these alarms were going off, assuming that because a different stakeholder was responsible for that particular piece of equipment, that would be sorted when it needed to be. So there wasn't a full understanding of the implications there. When a culture develops of just acknowledging an audible alarm because of the inconvenient noise it makes, these are usually red flags, guys. Process should be stopped and a full investigation carried out the minute that alarms are getting acknowledged, and it's been more than once that you've heard that alarm. Lower tiered members just accepting a senior member's instruction to acknowledge safety critical alarms is potentially dangerous culture and a key performance shaping factor also. So also, if you see lower tier members within an operational team are just acknowledging alarms based on the instructions of a senior team member without question, that's also red flags, and it should just be, you know, something that should be addressed immediately. Training and competency considerations are also to be looked at, and the operator does not have full understanding of the potential impact of you know, having these malfunctioning equipment or potentially malfunctioning equipment in the zone. And in this example, in fairness, they sent somebody out to have a look at those particular locations, but when they found nothing wrong in that location themselves, they thought that it was just a faulty piece of device, but it was just that the tags had been missed, and one zone was actually referring to a different zone on the HMI. So basically, guys, if in doubt, stop and check it out. That is the main lesson to learn here. And I'll hand you back over to Todd.
Thanks, Peter. So that was actually an example of one that didn't lead to a significant incident, but was stopped along the way. So now let's look at a process plant in Canada. In winter, the operator received a high-level alarm on a level controller that actually had frozen closed. So they got the high-level alarm. Based on that, they made a modification to the set point, and a couple minutes later, they got another alarm. Only this time, it was actually a low alarm from a redundant sensor, redundant level sensor. Now, the operator thought it was a high alarm, so they continued to reduce the set point down to 70. Made no other corrective actions for the next 8 hours, let the process run its course. And of course, the level of the tank continued to go down as they were drawing water out of it without any replacement going in. And it wasn't until 8 hours later that they started to see cavitation in the pumps to realize that they were at a low level situation. And unfortunately, they were not able to correct it before they ended up shutting down the plant. So they lost steam flow to a refinery or chemical plant in Canada in January. Not a good situation. So let's look at what caused that problem. So why did the operator take the wrong corrective action? Well, because they had redundant measurements on level, they actually had the benefit of easily cross-checking what was happening. So they should have been able to do that. Maybe they didn't know that that was something that they should do. So as part of training, that would be something that should be emphasized, that before you respond to something, you verify by looking at other available information that your action is needed and correct. There was also a failure of situation awareness. The way the HMI graphics were created, only the symbol for the level controller would change color to indicate the presence of an alarm. The level transmitter, the redundant measurement, did not change color to show alarm because of some discrepancy in calibration. Looking at the alarm summary displays, there was some problems with situation awareness there as well. There were actually a whole bunch of nuisance alarms, standing or stale alarms on that summary display, about 15 of them, which made it harder for the operator to detect a new alarm come in and truly understand what was going on with all the different information, the different columns that are displayed on an alarm summary display. It was hard for them to process it. And in particular, in this case, the only way that you could tell that the alarm that came in was a low alarm and not the high that the operator thought was for one of the columns to look at very closely and realize that it said PV low instead of PV high. Other than that, all the other information was identical. So again, it made it hard for the operator to see what the problem was. From an operator workload point of view, in this case, they might have not had enough work to do. They didn't remain very vigilant in their monitoring of the process. So it's thought that they perhaps didn't have enough to keep them really engaged. Now let's also look at how the organization responded to that situation. Based on their investigation, what they decided to do was to add some additional alarms. Add a low alarm for both the level controller and level transmitter, as if that was really the problem. So you can see that in this case, did the organization really learn appropriate lessons and build them in to prevent situations occurring in the future? I would say no, they did not in this case. Let's look at another incident related to a leak of a pump. So in this scenario, we have a sump pump that's automated so that it automatically turns on when it reaches the high alarm level and turns off when it reaches the low alarm level. So in this particular situation, the operator was transferring reagent into a neutralization area, and the reagent pumps began to leak, and that started to collect in the sump area, as well as it led to alarms in the neutralization area because they didn't have enough reagent. So the operator started to respond to the situation, focusing on the neutralization area, taking action to try and address the situation. During that time, they got the high level alarm, and then they got the high level alarm in the sump, and they ignored that. Ultimately, the sump overflowed, and it wasn't until the next operator came in from doing their rounds that they realized that they had actually spilled 10,000 gallons into the environment. So let's take a look at what happened here. Again, why did the operator not take the correct action? Well, they diagnosed the problem incorrectly. So in the detect, diagnose, respond pattern, the diagnose step was where it failed. They thought the problem was in the neutralization area, and they focused their attention solely there to try and address the problem. So they had a loss of situation awareness as well, because they focused their attention only in that process area. Now, they probably exhibited some confirmation bias as well by taking in additional alarms and measurements from the neutralization area and not realizing that they were not successfully impacting the problem by focusing there. Now, why did they ignore the high and high levels in the sump? Well, because the high level alarm was a nuisance alarm. Since it was used to turn on the sump pump, every time that alarm went off, it was a nuisance. So it actually conditioned the operator to ignore it, ignore that alarm, ignore any alarm perhaps from the sump area, and that impacted their mental model so that they didn't understand how information from what was going on in the sump could relate to what was happening in the neutralization area. So their mental model was wrong in that case. Now, why was that high level alarm in the system? Well, it had failed rationalization. That was actually a design fault. That was a design error. That alarm was not valid. There was no operator action required, and it was not an abnormal situation. So as we teach in the alarm management class, it would fail during rationalization and should have been removed. So having that alarm in there actually led the operator down the path to error and to an incorrect response. Looking at another incident, in this case it was a batch process where they made a modification right before beginning a batch run, and unfortunately it was not done correctly, so that the material got delivered to the wrong tank. A couple days later, a high level alarm was generated in the wrong tank. Operator ignored it. Next day, another high level alarm from the wrong tank. Operator ignored that as well. Production continued, and eventually they overflow the tank and dumped 1,000 gallons of material was spilled. And they didn't realize that until the field operator investigated. So what happened here? Again, why did the operator not take the appropriate corrective action? They diagnosed the problem incorrectly. They felt that the second tank was out of service, was not being used. So it was not possible that there could be alarms coming from it. So they dismissed the high level alarm as well. And again, for this particular scenario, had the wrong mental model or had errors in their mental model that didn't take into account that a piping problem could have led to material going into this tank and high alarms. And because they didn't realize that, they did not make the correct response. So what biases were at play here? Probably some overconfidence, because the operator didn't even seem to investigate why they were getting those alarms or false measurements to try and prove that it was an anomaly. They must have felt so strongly that it was a mess up in the instrumentation or the alarms, that there was no chance that they didn't know what was going on. So in that case, they incorrectly assumed that they knew what was going on. This is an example of what we call incidents that occur where the wrong equipment was targeted. And it's actually very common in industry. And this is one of the areas where, for slips and lapses as well, for expert operators, you can make some changes to the design to help prevent wrong equipment errors from occurring. So now let's talk about some key takeaways, some lessons learned from this analysis. And Peter's going to start us off with some key takeaways from his section.
Thanks, Todd. Yeah, just to kind of wrap it up, guys. Human factors engineering, when applied at the design stage of a project or product, can drastically reduce risk levels within a process. And that was, like we were covering earlier, engaging the end user, engaging the operators in the design stage of a project to ensure that we've considered human factors before we deliver the project, especially given, you know, if one particular system is only part of an overall system the operator is going to be involved in. We have to engage and make sure that our device or the design, especially around the HMI, is as usable and as efficient as possible for the operator intended to use it. Human factors reviews should be carried out dynamically throughout the project lifecycle and focus not just on the equipment and systems, but also on the human operator interacting with those systems. So let's not just, you know, focus, you know, on that our own particular equipment system. Focus on the operator interacting with that system and the overall systems. An operator is not always better off with as much process information as possible. It's highly recommended to provide relevant, actionable, and the right kind of information to the operator. So when we design our HMIs, we don't necessarily need to provide the operator with absolutely every process deviation information. We need to refine it, and as Todd mentioned, rationalize it to make sure that only the relevant and actionable information is in front of the operator, and it's classified and prioritized correctly. To have an effective system from where an operator can perform efficiently within, we should really be looking at the following: continuous training and assessment to become and remain competent. So just to reference alarm response, for example, you know, with the way that systems have gone these days in automation and Industry 4 coming through, there's so much available technology to provide absolutely every piece of information to an operator. But is that the most efficient and safest way to do it? Probably not. We need to provide them with actionable data, and we need to make sure that our operator is competent and trained to action that data. So if there is a particular process deviation that requires action, the alarm should be clear, crisp, and he should know exactly what to do in that situation with that particular alarm. So that ties back into our alarm philosophy documents and our alarm operator response plans. Equipment and systems designed with human factors engineering, engagement with the end user. We covered that in the first bullet point. Very, very critical to consider the human factors through the human factors engineering process at the beginning of our project and design. And number 3, organizational culture and procedural structure to ensure human performance. So another point that really want to stress as well, guys, is that it's very important to make sure that we promote a good organizational culture where we are monitoring human factors from a reliability and performance standpoint, to make sure that, because as a project has been delivered, there's a great chance that over time that particular focus has changed, the process might have changed slightly. For sure, the environment will most likely have changed as well. So we need to be continuously assessing the human performance factors that are affecting the operators in their environment. So finally, a human operator must be trained to be competent, and competent to become reliable. Only then can the reliability of a human operator be taken into consideration. Furthermore, the reliability of a human operator is also completely dependent on the usability and maturity of the human machine system from which they are operating in. So not just, have we trained the operator? Have we made sure that, his competency is up to date? Yes, but we also have to look at how mature our actual, the human machine system he's working within is. Have we put him in the optimum environment to detect, diagnose, and action anything that comes in? And have we done everything we can with all of our systems, HMIs, and setup to make sure that it's as clean and crisp as possible as well? And I'll hand you back over to Todd.
Okay, and some final comments from my side. When you're designing the system, make sure you're thinking about reinforcing the operator's mental model and situation awareness. That could include providing confirming information, like in the level issue that we talked about with the redundant transmitters, making that easy to see. We want to think about addressing differently how expert and novice operators use the system and respond and could make mistakes or make errors, and try and plan for that and plan around that or build around that as best that you can. And then my last thought, we need a new way to think as an industry. From a management point of view, we need to focus on not blaming the operator, and when we do incident investigations, not stopping when we get to the operator action as the root cause. From an operator point of view, in addition to understanding the individual alarms and what they mean, we also have to get operators aware of the fact that they can make mistakes or make errors based on their own cognitive biases and a loss of situation awareness. And they need to catch themselves if they are perhaps fixated on a certain solution or response which may not be true, including when an alarm doesn't make sense, rather than just disregard it, they should investigate. They should assume that the measurement is correct until proven otherwise. And then lastly, from an engineering point of view, human error is a part of life. It can't be totally eliminated. However, effective design can minimize or prevent it. So on that note, we'll say thank you very much. We want to kind of open it up for questions if there's time. I also wanted to mention we have an upcoming alarm management class, an online class, the end of April. It's 3 days, 3 half-day sessions. It includes the opportunity to take the alarm management practitioner exam. And then if you are interested in additional information, there's some videos and such related to previous exida webinars. And if you have questions or comments afterwards, there's the contact information for Ali, Peter, and myself. So again, I just want to say thank you for attending. Do we have any questions that we can address?
I don't see any at the moment.
Okay.
Just to re-emphasize, guys, if you do have any questions that pop into mind afterwards, as Todd mentioned, please reach out to any of us to follow up with you. And if something is a particular pain point in your operation at the moment, or even in your design, we'd be only delighted to help.
Okay, so on that note, it looks like we don't have any questions coming in. So yes, definitely, if something comes up, you think of something after the fact, please reach out to us. So on that note, we'll say thank you and have a good day.
Thanks, guys.